Okay, guys, so this is what we were going to go over today. We actually already went over the material from 2.3 because we were going to see a lot of interval and actually a lot of set notation, especially the squiggly brackets, and we were going to see a lot of function notation as we were dealing with linear equations. So, excuse me. Um, I wanted to review over this stuff, and now we're going to do a review over it one more time because um, basically our next unit is going over functions and different types of functions. All right, so first thing we're reviewing is basically we're going to look at a graph. We're going to find its domain in interval and set notation, decide if this is a relation and is this a function. So remember, if it's an interval or set interval notation, we write it in parentheses or square brackets, depending if it's equal to or not equal to. And then if it's set, we put it in the squiggly brackets. And then we're going to use a red to write in today. And then if it's a relation, if it can be graphed, it's a relation. If we can graph it on a coordinate plane because there's an x or an input value and there's a y, which is an output value. If it's graphed on a number line, it's not a relation because there's only one value. And then remember, if it's a function, it passes the vertical line test. So we can actually answer these two questions down here right now. It's graphed on a coordinate plane, so this is a yes. It passes the vertical line test, and so this is also a yes. So let's go with domain in interval notation. Remember, we always go from least to greatest. So our least value over here, you can see that there's actually two intervals. So our least value is negative infinity. And then what we're looking at is, I'm going to draw a line in green right now, is right here, this is negative 3. And if I draw a dotted line at negative 3, and we'll talk about actually what's happening right here a little more at the next section. But this is a line that on both the left and on the right side of this function, it's a line that both sides of the function it's approaching, but it's actually never touching. And this line is what we call an asymptote. And this is actually one of my favorite math words because as an LDS person, it's as close as I can get to swearing without actually swearing. I shouldn't admit that, but it's kind of one of my favorite words for that reason. And so basically the kind of the definition of an asymptote is it's a line or a value that a function is approaching without ever actually equaling. And so that's what's happening right here. So on the left side, it's getting really, really close to negative 3. So our greatest value is negative 3 without ever equaling negative 3. And then on this side, the least value is negative 3 without equaling negative 3. And then it's approaching infinity. And then it's the union between those two intervals. And so that's our interval notation. Set notation, we've got to write these as either two inequalities, or we can see that basically it's all these numbers. It's just we know that, hey, there's an asymptote right here. So we can say x, hey, it just can't equal the asymptote. And so we can just write a set as x is equal to a set of all x values such that x cannot equal that right there. And so that basically answers these questions right here. So if we move on to the next, now we have one where instead of an asymptote, we kind of have either, you can think of it as an ending point or a starting point. So there's this place where it starts and then the graph just goes. So in this case, when you have a graph like this, you want to figure out exactly where this coordinate is. So if we look at our x value is 4, and our y value appears to be negative 5. And that basically is going to tell us what we need to know. So with interval notation, we can see that we're looking at negative infinity for our domain. That's a really funky infinity sign. And then we go all the way to 4, and it's a square bracket because it can equal 4. And so there's our interval notation. For set notation, we write our inequality, and it's always x's, because we always want our variable first unless it's a compound, and then we write x in the middle. So we've got x, and how does x compare to our starting or our 4? And since that's the number, we don't compare it to negative infinity. Well, x appears to be less than or equal to 4, and now we just write our set notation around that inequality, and there we go. Is this a relation? Well, it's graphed on a coordinate plane, so that's yes. Does it pass the vertical line test? Yes, so it is a function. All right, this is what we call an ellipse. It looks like a circle, but it's been elongated horizontally. So let's go, we can go first. Notice in this question we're asking about the domain and range, mainly because domain, remember, is all x values and range is all y values. I did the range because the range is really easy to identify in this too. Is this a relation? Yes, it's graphed. Is it a function? No, because it does not pass the vertical line test. We can see that just right there. So, just for example. Okay, domain, you can see we can go right here where we've got -4 to right here, which goes to 6. We go to the widest part of a graph like this. So we've got from -4 to 6. Okay, this interval goes from a number to a number, which means our inequality is going to be compound. X exists between these two numbers. And remember, compound inequality like this is written in this way, where we use less than or equal to as our inequalities, and we put x in the middle. And then we just write our set notation in there. I didn't leave myself enough room for all of this. And so that's our domain. Our range goes from 2 to -6. So, sorry, I should say -6 to 2. Square bracket there. And so I'm going to go -6, 2. I really should give myself more space here. -6, 2, put y in the middle, less than or equal to, less than or equal to. Y is equal to a set of all y values such that, and close, and there is our range in set notation, and that's how we do that. Okay, finally, another way that you're going to deal with these problems is that you can be given the equation, and then you have to be able to find the domain in interval or set notation looking at the equation. So first of all, basically when it comes to these types of problems, you got to be able to look at the function, and you got to think to yourself, is there something about this function that is, when I try to evaluate it, it's going to be limited on what I can do. For example, on f of x, what kind of numbers can I not take the square root of? So I know I can take the square root of positive numbers because anytime I square a number, I'm going to get a positive value. I know I can take the square root of 0 because 0 squared is 0. But I cannot take the square root of a negative number. So what that tells me is if I want to figure out what my domain is, I'm going to take -2x plus 10. I'm going to basically say, okay, I know my domain has to be greater than or equal to 0. Because everything, if there's going to be a solution, it has to be 0 or above. So that's what I'm going to do, and then basically from there, once I figure out what x is going to be to make that true, I just set that answer up in interval and set notation. For g of x, I have a fraction. Well, what can I not divide by? I know I can't have 0 in the denominator. So what that means is I've got these two values here that I am multiplying. So that means either x minus 2 can't equal 0, or x plus 3 can't equal 0, because if either one of those equals 0, then I'm dividing by 0. So that would mean that x cannot equal 2, because if I plug 2 in there, I'm going to be dividing by 0, or x cannot equal 3, or sorry, negative 3, and that would, because that would mean I would be dividing by 0. So that would be the limit to my domain right there. And honestly, in the case like this one, I wouldn't even bother. I know the directions say right in interval notation, but when it's a cannot equal type of domain, this is so much easier to write in set notation. So I would just do it that way. Then finally, in this kind of problem, I'm just going to kind of point out something. Usually also, so like I told you guys, with the square root, you think to yourself, okay, I can only take square root of positive or 0. And with this, I can only divide by, you cannot divide by 0. With h of x, I can square all real numbers. I can multiply 5x by all real numbers, and I can subtract all real numbers by 7, right? There's no limit to a number that I can square, a number that I can multiply by 5. So this means that my domain is all real numbers. So when you look at a function, you're like, okay, I can put any number into this part, I can put any number into this part, and you really want to look at things and be like, is there any limit to any part of this function that's if I put a number in here is in for x, is there any number that I can't put in? Then if you can't find some limit to the domain, or some number that you can't put in for x, then that means there's going to be all real numbers. And that's basically what we're going to do for this section. Now I'm going to, after you guys watch this video, I'm just going to go ahead and start working on the homework problems.